Often when we think about the universe, we usually think of all the things we've discovered so far. But when you actually start asking yourself everything we don't know, it can sort of be an ominous take on what the universe as well as life really is. So here's at least 10 reasons why the universe is scary and majestic at the same time. So number one is the illusion of distance. Now, the illusion of distance is a very interesting principle. When you look at everything we've discovered in the universe and beyond that, you basically can look at it like this. Every object in space has a definite size, but you also have the distance between where we're at to where it's at. Every object we've ever discovered in space, chances are we've always had this conundrum or this principle that we try to figure out of how big these objects really are. Now, there are obviously advanced formulas that scientists use, but there's always been this idea that perhaps it's even larger. For example, the objects that are the furthest away are usually the hardest to measure because of how inconsistent they really are. Because again, everything in space moves, and we don't really know how big these objects are, how far away they are. It seems like if we can't figure out how far away they are accurately, it seems like we might not be able to figure out, like even with a zoomed in ratio, what these are. So take into account like our galaxy, for example. Our galaxy, we are obviously inside the Milky Way galaxy, and if you ask a lot of people what they think, you get a lot of different answers on just how big our galaxy is. Our galaxy, if you were to go like 30 years ago, a lot of people used to think that the Milky Way galaxy was 100,000 light years in diameter. Now, if you don't know, 1 light year is 5.88 trillion miles, and 1 mile is basically 5,280 feet. Now, the way it works is if the Milky Way galaxy was to technically be bigger than what we think, then that basically would make us reconsider everything else in space too. Like, for example, if the Andromeda galaxy is to merge with the Milky Way galaxy, then this would prove that the Milky Way galaxy has to be somewhere around there too, if they're basically the same size, except the Andromeda galaxy is said to be slightly bigger than the galaxy. So if our galaxy is bigger than we previously thought, then the Andromeda galaxy has to be even bigger as well. And so now you create this illusion that if all objects that we've discovered so far in space, their average distance is either further or closer than we actually think they are, then this proves that everything else in space is really just, there's a lot more out there than we can really mathematically figure, unless we put in more time to develop like some kind of a star map, which there have been simulations of, where we can basically understand what we have discovered and what we haven't discovered yet. And believe it or not, if so for example, if our Milky Way galaxy was at least 2 million light years or somewhere around there, then that would basically mean that our galaxy is like 15 times bigger to 20 times bigger than 100,000 light years. In this case, it would be 20 times. But if that is true, then that basically would also mean that maybe there's 20 times more mass, 20 times more stars, 20 times more. And you really can see the idea that we really don't know everything. It's possible, like, even when our galaxy was considered to be 100,000 light years, they said there was at least maybe 100,000 to 400 billion stars in it. Well, if there's like 15 to 20 times more mass than that, then you're basically looking at, it's even more harder to accurately measure because nobody's really figured out the true diameter. So if that's the case, then where do you begin and where does it end? And how many more stars and how many more things can be filled inside the void that is the Milky Way galaxy? And that's just one galaxy, considered all these other galaxies that are out there, So it makes you wonder, how much further away are they? How much bigger are these objects? And not only that, how much bigger is the observable universe compared to what we think it is, and other universes and beyond that. And so now you can see why the concept, even if it's just estimations, can be truly terrifying. So number two, what we consider to be like probably one of the most terrifying things in the universe is basically the fact that everything in space moves. Everything in space moves at such a velocity that even we don't really fully understand it, even with theory of relativity, which is fact in this case. I mean, the fact that every object in space moves so fast, like it's faster than what we're used to seeing, it really makes you wonder how every dimension is different. Like the second you leave this planet, it's completely different. You know, even the way this planet orbits, it doesn't feel like it's moving, but it is. And it's orbiting around a star while it's moving in space. So the star moves, the Earth moves and orbits around it, rotates, like all this mathematics. You know, otherwise the seasons are all changed and everything just gets all distorted and warped. And that's just weird to think that that could happen, but it hasn't to us, you know, because our mathematics with our planet just, it's caught in the right loop. And we haven't, like a lot of people just don't seem to realize just how fortunate this planet is that it's able to keep doing that, because that's how it is from the distance that it is from the sun. I think it's 93 million miles or 150,000 or 150 million kilometers. I think 1 kilometer is basically 1.6 miles, or 1 mile is 1.6 kilometers. Yeah. So just to, if you're, depending on what metric system you use, I use both, because it's really interesting. It really is. Things with zeros are definitely a lot easier than just calibrating decimals, but fractions and wholes are interesting though. So yeah, so everything in space moves so fast that you really can't comprehend everything until you really sit down and think about it. And even then it makes you wonder just how fast is everything moving in space, to the point where there really is no such thing as a fixed speed as long as there's nothing holding it back. Even like the acceleration of the universe has been debated, and even at the same time faster than the speed of light, because nothing has ever slowed it down. As a matter of fact, if old theories really are correct, and I mean, it's really hard to accurately measure this, then that would mean that the observable universe, as well as the, well, not the observable universe, but technically our universe, and beyond that, would actually be much further than what we've ever speculated, because there's always been this debacle that the observable universe was, or not the observable universe, the universe was slowing down at some point. But then you have scientists that believe that was never the case. It just kept picking up faster and faster, and it just got faster and faster, and it never slowed down. Faster than the speed of light, and even faster than, what is it, faster than gravity. Number 3 has to be the average temperature, the crystallization, I like to call it, of the universe. It's like negative 454 degrees Fahrenheit or Celsius in the universe. And this is in the empty space voids parts. But the thing about that though, so like liquid nitrogen is like just a little under 270, but like to think, or somewhere around there, and you're looking at like, you got such crystallization methods in space. Like that's how rocks are formed in space. They basically crystallize, and that's why you have sheets of ice flying in space. Rocks are formed. I mean, that's how planets basically start. Everything, before everything starts warming up, you basically have, everything's cold at first, because you have a universe that's cold and hot, depending on the photons, which are light particles, and then dark matter, or radiation in this case, that's not concentrated, or not concentrated, but it's just cooled and cold. So because of its darkness, it's radiant, it's cold, and light is basically hot, and you know, you can see it warm. But it's interesting to think that the universe can be that cold, and at the same time though, we're still here on this planet. And because even if our Earth is 93 million light years from the, not light years, 93 million miles from the sun, you know, we can still, you know, stay warm because of the light and then the atmosphere, which is really cool actually. When you think of, like, compared to like other planets like Pluto that are so far away, and it's like, even when it's facing the sun, it's like negative 90 or 200 and almost 200 degrees below zero, which is interesting. So number 4 would be black holes. Black holes are obviously no introduction. You know, these things move in space, they suck things up, and then where does all that energy go? But what's even scarier about black holes is there's been this argument that's been popping up a lot more over the years, that gravity has proven itself to be stronger than the speed of light. And how this works is, the idea is very simple. If light itself, moving in its, original speed, in this case it would be 300,000 kilometers that we know of. It's possible it could be faster than that because we can't really accurately measure something that fast. But if that is the case, though, then again, we could say it's bigger, it's stronger than that. So that's like 100, I think it's 186,000 miles per second. 300,000 kilometers, somewhere around there. So if that is the case, then you're looking at roughly, so the universe would move at such a speed, and these black holes would also be moving and being able to absorb things so fast that even the speed of light couldn't take it. And it's interesting to think, because that would mean that moving through a black hole, the energy that survives the intense pressure then is going even faster. And this would explain why the speed of, like, if there is a big bang of some kind in multiple universes, let's just say, this would also explain why black holes create new universes, because that energy has to go somewhere. And what's strange is, it would make sense that all of the energy that gets released through the other side of a black hole, however big that is, how long a black hole is, it really would make you think that it's scary to think that something like that can traject. Because if you stare into a black hole, you don't really see the other side of it, because it's just no light mixes with it. Everything's moving so fast, it doesn't hold it, and light doesn't mix with radiation. So if a black hole is nothing but pure radiation, then dark matter, whatever, darkness versus light, it's a very cold experience, even if you are moving really fast and friction picks up. Something to think about, that black holes, there's tons of them in our galaxy, but there's so many more that could be flying around out there between galaxies as well. One thing that I also was always scared about reading was number 5 was supernovas, or basically big explosions, the opposite of a black hole. I didn't explain this, but black holes are basically when stars implode on themselves. Because of intense gravity, it creates a vortex, and therefore that's why the gravitational force is so strong to begin with. It's interesting how that works. Basically, an explosion in this case would be what a supernova is. It creates all this massive wave of energy, and it basically incinerates everything in a giant ball of gas. Now, I put it this way: if anybody remembers Ocarina of Time, The Legend of Zelda, when you use Din's fire and it shot that ball of flame like in every direction, it basically would be like something like that, but on a much larger scale though. So basically, when a star blows up, it basically shoots out plasma in every direction possible. I think it might, not to get confused with a gamma ray burst, but basically you're getting incinerated by intense heat and radiation even before the heat itself touches you. And that's how insane to think that a star is. It gets so hot, and there's certain elements not holding it together, it just blows up at its core and therefore expands out like that. Even before, and what's even more nuts, some stars can get bigger before they blow up. And the bigger the star, the bigger the bomb. Yeah, well, in this case. So the energy, the kinetic and potential energy that comes from this is so massive, it can destroy and create so much more energy that over time, that energy will eventually be recycled into the universe and then maybe create more stars, planets, and etc. later on. And that's actually very interesting to think about. So, and what's also even stranger, even until recently, it's possible that a star can create a black hole and a supernova at the same time. Now that's something that's kind of hard to explain, but it's interesting though. It's mostly due to the mass and the timing of when it dies. And also another one that's really scary to think about, number 6, would be a gamma ray burst. Now, gamma rays, believe it or not, are not the same thing as a supernova. Usually when a star collapses just before it either turns into a neutron star or a black hole, the star can give off what is known as gamma ray bursts, like these big bright balls or bright beams of light that can incinerate just about anything that it touches. It's basically the truest light form of photons that you can never really see because they happen so fast, and they happen like, it's like the definition of lightning. It traverses so fast, it can last from like within milliseconds to, like, no joke, like maybe even hours. But they're like billions of light years away from the Earth. We don't ever get a chance to see this, which is why I do believe that, you know, going back to what I said earlier in this video about how stars can be bigger and everything in galaxies can be significantly larger. There's so many more stars in just our galaxy, and there's even so much we haven't discovered yet. So it's possible, like, you know, if our galaxy is even bigger because we haven't discovered everything yet, that it's possible there could be trillions of stars. Again, it's still, we don't really know everything. So with how much we don't know, you know, there could be so many gamma rays flying around our galaxy right now before they're short-lived that we don't get a chance to really see because, like, they're so far away that our telescopes can't pick them up even from so far away. Or maybe we're looking in the wrong places. But basically, if you ever did get a chance to capture a gamma ray burst, you basically would be seeing these big balls of bright light that are like, I think they said it was like million trillion times bigger than the sun. And they're so fast that, again, they just incinerate everything in a large, it's like a giant laser that you see, like a just giant photon light. Keep in mind, blue flames are like the hottest, and white flames are the second hottest. So whatever temperature that is, off the top of my head, I don't know. It's like I don't even know. Gamma ray bursts could be, I forget exactly what the temperature of them are, but you would not be you don't want to get hit by one of those. I mean, it doesn't cover as much range as, like, let's say a supernova. It blows up and then it just incinerates everything in its path. But basically a gamma ray burst is whatever beam of light, however thick it is, and it just goes flying in whatever direction. Not to get confused with something like a solar flare, which, if you're familiar with those, but it's just, again, one of the most dangerous things in the universe. You know, the radiation and the electromagnet sphere that the universe seems to create. There's a lot of electromagnetic material flying around in the universe, which is just crazy to think about. But man, that's incredible that a planet can be vaporized just like that and not even know that could have happened. Okay, and so number 7 has to be solar flares itself. Okay, so solar flares are, okay, try to do the best I can to explain this. So take the definition of the sun. The sun is nothing but a sea of fire, plasma. So solar flares are basically like, they can like erupt from the sun and they can go flying into outer space. Again, it can like incinerate things. However, though, that's not all it can do. Even if the flame itself doesn't touch things, it basically can create this interruption. It's like a giant magnosphere, kind of like a giant EMP field, electronic pulse detonation. What it does is it can create like some kind of blackout. It can do all sorts of crazy things with the amount of energy it gives off, whether it hits something or whether it just burns it away. I mean, it's like basically parts of the sun that are going, but every star can do this because they're made of plasma. Or basically big balls of fire in this case. So to be able to have to worry about something like that, that itself is probably the closest thing we have, aside from the sun just physically burning things up if it got too close to this planet. Or, you know, because again, you know, you can go outside and see the sun on a visible day, but it's still 93 million miles away from the Earth. That's how you know that you're dealing with a very big object in space, because of how far away it is. And that much we do know. So that proves that the sun is obviously bigger than we think it is. So the sun is able to burn things to a crisp, but at the same time, though, it can also cause some kind of pulsar interruptions that could basically destroy like electronic grids, or heck, even this whole planet if it wanted to, really. It's crazy. It's nuts to think like what the sun's powers enable it to do. The elements of surprise and the elements of nature. Probably something else to really think about when you really think about the universe and everything that flies around in it. is basically physical impacts from, like, whether it be asteroids or comets or meteorites or planets, if that ever came down to that, or just things colliding with one another and just causing such a huge form of destruction that, nobody really sees it coming. I mean, the one that I remember when Russia got hit by that one asteroid, or maybe it was a meteoroid, I gotta remember, and it killed, I forget how many people, but nobody saw that coming because that thing hit the earth so fast that it just created a huge impact around wherever it landed. And it's scary to think that could happen at some point, but when you mathematically think about it, it's unlikely still. But to think that all objects in space move so fast that they can either burn up in the atmosphere before they even get down here, but then at the same time, how fast they're coming from so many different, like, there's so many things flying around in our universe and even our galaxy, because here's another thing to think about that's really interesting. I mentioned before the crystallization method that we have in our universe, in our galaxy too. Everything's formed through, like, some kind of icicle methods, like crystallization. You take planets, they're no different. They all start off as a rock, and then before they start forming their gases and everything, over time, but they all start, like, through, like, some kind of a crystallization method, because over time what's going to happen is these rocks are going to form, and they could be anywhere. Like, when we look at our solar system, we want to think that there's really not too much stuff in between, but that's not true. You got, like, the first asteroid belt that's between Mars and Jupiter. You got the next asteroid belt, which is somewhere between Uranus and Neptune, or maybe it's Pluto. And then if you get into the cubular belt, which I'm not sure if you want to say is still within our galaxy, or within our solar system, sorry. And then you have what is known as the Oort cloud. And the Oort cloud is, like, between here and the other solar systems. And so it makes me think, how many other asteroid belts are there between other galaxies and solar systems, and what about all these objects that are in between the main, like, stars and all that? Because usually when you break a galaxy down, the next biggest thing would be stars. How many stars are there in between, the average distance between them, and then you try to figure out, like, what orbits between all this. And what's interesting is if you were to take, like, original like space travel fantasies, science fictions in this case, they always have the idea that when you traverse through the galaxies, you can just go so fast through, like, one galaxy, or through, like, one direction. But the thing is, if you're traveling very fast, you would need, like, very strong solar shields in order to bypass crashing head on into, like, other rocks and all that are, like, we're flying into, like, not just asteroid belts, but comets and maybe other planets too you might even run into. Just in between the space of time and space, between the solar system you're in to the next one, and in between that as well. And that's something to think about. It's actually kind of scary to think about. And this isn't really one that gets brought up a lot, but it would be, number 9 would be the pitch black darkness that is radiation and dark matter. Because even if we could traverse through the universe, you really, like, imagine this. You're traveling super fast, faster than anything on Earth, even faster than the planet itself, let's just say, but you can't see what's in front of you. Yeah, that's true, because we use light amplification in order to see, like, light particles bouncing in our retinas. We can see around us because it makes sense. But even when it's dark outside, you're still kind of familiar with the area. You still got to watch where you're going. But when you're in space, not only is it something that we're not completely sure of, you'd be in places you've never seen before, but you can't see anything out there because the light doesn't mix with the radiation or the dark matter. It's cold, it's frigid, you got stuff flying around that could hit you, could kill you, and you wouldn't even see it coming. And not to mention no gravity, so you're basically whatever direction you're swimming in or floating, levitating in, pushing yourself towards, you got that jet propulsion acceleration you have to figure out, or whatever you use to accelerate in space.
So that would be something else to think about that's also very interesting and pretty scary in the nuts. And this one might sound like an overgeneralization, but this is actually something to really think about too, and probably the biggest one. And kind of going back to number one, where like the universe, you have like the illusion of distance, but this is basically talking about everything, everything in comparison. So while we have our methods to trying to figure everything out, but it's still no match for the fact that the universe is infinite and beyond. Or even if you were to leave this galaxy or this universe and somehow go to another universe, you would basically you would have no understanding of where you're at. It'd be just like you're starting all over again from start to finish. The universe, I can definitely guarantee you this, and I'm not somebody who studies the universe for a living, but basically I've always wanted to be a cosmologist or somebody who really wanted to put Carl Sagan's work into perspective more. And I remember Carl Sagan always used to say, like, one of the biggest things that we really underestimate as humans is that we really don't know how much we really don't know. Like, there's old sayings where, like, the more you learn, the more you don't know, the more you really realize you don't know. And it's true. If the universe really is much bigger than we think it is, and just how much bigger it really is, then what about like every other dimension? What about other universes and whatever the universe itself is inside of? It's interesting. And say you're somebody who believes there's different dimensions, like the fourth dimension, the fifth dimension. Where does that begin? Because basically it's just another line of symmetry that the third dimension doesn't have. And then, but it's like the further out you go, the better chance you have of entering a more powerful, complex dimension. And that's even bigger than the previous dimension. So if that's correct, then basically everything we think we see, we don't see. And it just goes to show you how much even we don't know. Even if you were just to focus on this universe, I've heard so many different things. Even our universe right now could possibly be more than trillions of light years in diameter. Even if, and that's not even the observable universe. Even the observable universe could go anywhere between, I've heard, 98 billion light years to like something like 7 trillion light years, which is basically 250 times bigger than 98. And then you also have like it could go up to 23 trillion light years, 30 trillion light years. These are all just estimates that I've heard over the years. And I mean, it just really goes to show you that like there's so many research papers that get published every day by so many different people, and even if you just type it in on Google or like even whatever search engine you use, you'll never find it unless you're really looking for this stuff, and even then you probably don't even know it exists. But it's weird to think that there's so much we don't consider, and just having something to compare it to, what we know versus maybe what somebody else might know, how far off are we really? And here's something else to think about. If we are wrong, as the human race is wrong about how fast the universe has been expanding and it never slowed down. I was reading somewhere it could have been somewhere between, it was like 500 or 100 like quintillion or something like that. Quintillion light years, quadrillion, quintillion. Um, but it's just, yeah, I think it was 100 quintillion. But it was basically like it was like either the next three digits or the next six digits after a trillion, and it was basically like suggesting that like all of our estimates would have been much smaller than previous, and everything would have been so much further. Because if you like, because the way acceleration works in space, there's usually a counterbalance between objects pulling things back and things just going in a certain direction. You want a good example? Look at the moon and the Earth. The Earth's ever since the moon crashed into the Earth and it was formed through its gravity and its orbit, the moon has been slowly traveling away from the Earth. It bounced off the Earth and it's slowly going backwards, but the Earth's gravity can't pull it as fast as the moon is accelerating. But because there's that plus and minus between how fast the moon is moving and the Earth is pulling the moon back, eventually the moon's speed is going to go flying so far back because the Earth's gravity is getting weaker the further out it goes. And wherever that's at, then it basically means that the moon's getting like an inch further every year or a foot further away than it previously was. So its orbit becomes a little bit longer. And it's interesting to think about that. Same thing goes with everything else in space. You know, if there's so much more out there waiting to be discovered, if there's so much more we don't know, then that just means that there's more opportunities out there. And also can be scary because, you know, so many things we can't suggest. You know, or it'd be like an episode of Rick and Morty. You know, Rick and Morty go through a portal and, you know, they just end up somewhere that no human being has ever laid eyes. You know, what is that over there? You know, what the hell is that thing over there, Morty? You know, just to point out a few things, you know, but it'd be interesting to think about, you know, what you take everything we don't know, you take everything we do know, compare it, and it's just how much further we've come in so many years. Even if it's like something out of like Stargate Atlantis, Star Trek, or Star Wars, you know, there's so many other civilizations out there on other planets just doing their own thing, or they could be traversing through like other planets that they found, but even they're still trying to figure out whether for the resources or just trying to make sense of the lore and trying to figure out, you know, what else is out there versus what we do know. And in the end, it just becomes a project of progression. What do we know and why do we exist? Because everything's unique in its own way. If you made it this far, thank you very much for your time. If you don't mind, please consider subscribing and donating money. Please help me do this full time. I do enjoy educating people, and I'd be looking to do this as a full-time job if possible. I hope everybody enjoyed this video, and if you did, I hope you have a wonderful day, and please come back again.